Welcome back to the A-Star Starship. My name is Kale, founder of the A-Starship. Today we're still working on the ASCII Data Specification update. Groundhog Day going on. I have been working on it off stream a decent amount. I've identified the problems that I need to fix in order to close out the milestone. And then I'm building a CPU neural network based random number generator, which generates pseudo random numbers by XORing the results of all the floating point divisions, which is pretty random. And then what are we doing? Let's see. I had to take down the live stream because I was going on too long of a rant, but I have this super cool new SGRATE, which means spectral graph token pre-transformer. Figured out some quantum physics that allows us to optimize LLMs into a smaller amount of memory utilizing a Laplace matrix diagonalization trick where you push the zeros in the upper right and lower left corners, and then you put all the numbers, all the one or the negative ones in the center or in the diagonal. And this makes it so that you flip the columns and the rows, and then you can move them in the diagonal, and then it makes it so that words that are similar to each other, the dot product space is closer together as opposed to spread out in the memory, reducing the memory footprint and allowing for some biochemical AI utilizing some sort of thing that I'm going to make. I don't know. Just pay no attention to the man behind the curtains. You can find the API at A**starship/script2, and this is the thing that I'm working on, and I'm not supposed to work too much on this, but it's okay if I messing everything up with my keyboard shortcuts here. So this is my innovation, and I'm going to make it so that it's not like a half hour long like last time because I went on way too many tangents. So imagine this paragraph is a graph like this. Okay? This is a Laplace matrix. What you do is wherever there's a node, there's a connection, like from 4 to 5, you put a -1. If there's no connection, like 5 does not connect to 6, right? So you won't see this connected in here. Like 1. 1 is the easiest one to find, right? And so it's connected to 5 and 2, right? Right here, 5 and 2. Why isn't there 6? Oh, because there's a whole row missing, right? Sorry, my fault. So the goal is for each paragraph, you parse large corpuses of data, and then you want to fill up a square graph. So I'm going to parse up related content until I fill up the number of paragraphs that is equal to the number of tokens in my LLM. So for instance, if I'm parsing dentistry, I will parse everything related to dentistry. And then if there's anything, once I fill up an entire matrix, then I will make other matrices out of sub-related subfields of dentistry. So for each paragraph, I am going to put a -1 if that token contains. Imagine the x-axis here is the LLM token numbered. And let's say this is a 6 token LLM. All right. And then I would parse 1, 2, 3, 4, 5, 6 paragraphs, and then I would fill up my Laplace matrix. All right. And then the on the diagonal is the number of nodes in the matrix. You put a -1 if the node, if the column contains that graph node connection, and then 0 if it does not. So what this correlates to, let's say we parse this paragraph right here. So we tokenize it, and then in this token, in this so first off, we're not gonna be doing we're gonna have to have 1 token per each unique word in the language. So we can't do the reduced dictionary like you do with the normal tokenizations techniques for the LLMs. We have to do the whole thing, and then we just preserve the order for the smaller token sets, where you break tokens up. So like instead of having like run and running, you have run and then ing, break it up into 2 tokens, and this reduces the number of tokens that you have. So we need we take out like things like ing, I think. Maybe, well, hold on, I'm gonna have to walk that back. We're just gonna take out things that are like ing and able, different, things in English, like so when you split the tokens up, we'll just disregard the last one, and then we'll just use the first one, and we'll probably have to test both to see which one works better, because I don't know, I'm just kind of theorizing here. So what we're going to do, so each of these tokens, it's like a bag of words. So if so each of these rows in the Laplace matrix is going to be 1 paragraph, and then it's a bag of words. So we don't count the number of instances of the word, we just see that the words are in there. And this is beneficial for neural networks for like the first stage of the neural network training, because when you don't know what the neural connection weights are, then just the fact that these words are connected, like cat and tree are connected, cat, litter box are connected. Okay? So then we push these zeros out into the corners. So there's like, the upper right and lower left hand corners. Put the -1s around the diagonal, and this makes it so that when we do a dot product calculation, that these dot products are going to be around the the token squared value, instead of it being spread out. So like let's say the tokens are spread all the way out so that there's like -1s over here and over here. This means that it's going to take up the most memory possible with when you start doing your transformer architecture, because you're going to do the dot product of self-attention, and then the dot product for the self-attention is going to be spread out as far as possible. Because the dot product for the attention then gets run into your transformer, or sorry, yeah, they get fed into feed-forward neural networks that are fully connected layers, and the information is not stored in the dot product self-attention transformer mechanism. It is stored in the weight connections in the neural network, and it's kind of like a network switch. If you can imagine, like just because you've done a dot product on a bunch of tokens, and then you've arrived at a location in the LLM dimensional space, multi-dimensional space, doesn't mean that you've that doesn't have information. This is the place for you to store the information so that you could take the self-attention, and then you can then pair that up with the data that you've then trained in the weight matrix, or sorry, in the fully connected neural network layers. So what does that mean for, okay, so what I'm doing with the Laplace matrix, we do the spectral graph theory, and spectral graph theory is used in quantum mechanics to calculate the energy transfer of quantum mechanical systems. You can, you got these graphs, right? They have subgraphs, and you got to think of it in the quantum mechanical system like, think of let's just take a two-dimensional field of atoms. Let's say there's atoms in every field, and these atoms are vibrating, and they could move to any of the adjacent cells at any time, randomly. This is the core fundamental of quantum mechanics. Now, over time, you're spread out with the highest entropy level. The highest entropy is the amount of order in the system. The lowest, it goes from highest entropy to lowest entropy. The highest order to the most spread out. And I always confuse them. In fact, I might have actually mixed them up. You should probably go look it up. Don't rely on me. But I utilized. Oh wait, I don't want to get ahead of myself. I have a physics theory that I base this off of. That's very interesting, called gradient relativity. But I'm not going to get sidetracked. So, in the quantum mechanical system, you're going back to our 2D field of atoms. Let's spread them out equally again, and then let's swap out some of the atoms with different elements. Okay? Just at random. And then these things are going to start vibrating, shaking each other around. They're going to start separating. They're going to start combining with each other, and then they're going to make these molecules, right? So to use spectral graph theory in quantum physics, you generate these subgraphs from the different atoms that are connected to each other. And so let's take the example of annealing steel. So to anneal steel, and forgive me if I'm not saying the right words, I'm not like a quantum physicist or a chemist, and I'm not a biologist, but I do know what a woman is. So sometimes I will mix stuff up backwards because I'm primarily a software computer engineer who goes down rabbit holes and grew up around a quantum physicist. So when you are making steel, you are taking iron and then you're introducing chemicals into the steel that you have to get inside of the steel. I think it's called annealing. Let me verify that because I don't want to tell you the wrong thing. Yeah, heat treatment. Yeah, I'm using the right word. So you heat the steel up, and you put the alloy in it. And then as the steel is vibrating around, the elements in the alloy material that you added will mix in, and it will form steel. This is the best explanation as to what I'm doing. So you would calculate the flow of these atoms through stochastic statistics, randomness. This was how they discovered quantum physics in the first place. Very interesting story. I think it was Rutherford who figured this out, but I'm not sure. So what you do is you imagine the alloy in your steel is like a subgraph. So you put in a bunch of alloy in one area and everything is connected to another area. You don't know what these connections are. All you know is that there's a connection and that they transfer energy between the different nodes when it bangs around. So what we do is we take our Laplace matrix for our nodes. Just imagine it's in 2D. We have a 2D field of atoms. We made a Laplace matrix where, let's say we have a nickel atom. We're putting that into steel. And then in each place in the matrix where there's a nickel atom, we would then have a -1 in it. And then everything else is steel. So what we would do is calculate the determinant of not the determinant. We would calculate the eigenvalues. We're going to take the largest eigenvalue out of this matrix, and then we're going to multiply the matrix such that AX equals lambda Y. Okay, so we have our matrix here, and then we're going to add, where is it? Over here, we're going to add our X. So imagine the Laplacian matrix is A, and then we're going to add an X over here, equals lambda Y. So now we're going to take the inputs, find the largest eigenvalue. What this corresponds to is when you do the AX equals lambda Y, you are stretching X by a certain factor to get a Y. right? Just imagine it in the 2D sense. Like I have a 2x2 matrix, multiplying it by a 2-element vector, and then I'm going to get lambda y. So I'm going to, whenever I go do this transformation and I go a little bit, let's say I have a 10% stretch factor. My eigenvalue means that I'm stretching. I have an eigenvalue at 5. Okay? So, or sorry, eigenvalue of 1.1. This is going to correspond to whenever I go over 1, then the y value is going to go up 1.1 because it's a stretch factor. That's what an eigenvalue is. That whenever I have done a linear transformation, I have then stretched the x to make the y. So with our quantum mechanical system, we are using this in order to make the nodes that connect to each other and have the most influence on each other be much larger than the rest of the nodes. So whenever we run our statistical calculations, we square it, and then all of a sudden now the connected nodes are going to be much larger than the other nodes, and when we do our math, then the other nodes will not affect the outcome of the calculation as much as the dominant nodes. And since it's all statistical certainty, we're going to square it, and then we're going to then take the square root of that, like you're doing a standard deviation calculation. So what does this mean for the LLM? I think I'm doing good. I've almost explained everything in 20 minutes instead of my extremely long one last time. So what this means is that we're going to make a transformer, a tokenizer for script 2. This is going to be, and then the neural network based random number generator that uses a running XOR of all the all of the post floating point division calculations. So I do a floating point division, and then I XOR my running XOR with it. And then I do that a bunch of times when I'm calculating e to the x, and then I keep my input in a certain range, and this allows me to use an optimized e to the x algorithm to where I can load my first guess based off of a table of pre-calculated e to the x values. Because I take the inputs from -1 to 1, I take 12 of them together, 12 random numbers between -1 and 1. I think they need to be non-zero. I haven't finished the algorithm yet. Pretty sure they need to be non-zero, but I don't know. So we do a running XOR of us each time we want to calculate a random number. We're going to keep track of the last 12 random numbers. We're going to replace the last recently used sample with the newest sample in a circular buffer. Then we're going to run e to the x 1, 2, 3 times, because each time we generate a random number, we got to run a certain number of calculations. So we're getting a certain number of e to the x calculations each time. Plus, we want to add some salt on it. Rub that shit up in there so that you can't tell. So that none of these... See, because we don't want to have a problem with similar number patterns causing the bits to not do what we want. So we need to combine, we need to XOR bits from a variety of different calculations. Like, we don't want to just continually do e to the x. You know, like, let's say I have a good e to the x algorithm that has a good lookup table. Because I'm using a limited range, I don't have like the full range. You know, so then I can like, I'll run e to the x in a loop using Newton's method some number of times. Okay, shouldn't have to do it more than 2 or 3 times because we started at a good place. Because we started at a good place, you know, we can get away with only having to run like 4 division instructions maybe. So then we got to do the standard deviation calculation. You know, that's going to require, you're going to add up all the samples, you're going to divide once there, you're going to do your square root for your standard deviation. So you take the, you know, the x squared minus y squared, sorry, the mean squared. Which one is the thing? I can never remember, dude. I think you take the standard, yeah, the standard deviation. Yeah, the mean. You take the mean. That's going to take one calculation, and then you got to square up your samples 12 times, then divide once. Then we're going to take a square root. And then the square root again, since we have a very limited range in our input, we can use a good lookup table on it. So again, we'll have like maybe, you know, 2 to 4 cycles through the loop. So we're looking at maybe 12, 13 division instructions to calculate up a random number. Like, that would be so sick. That would be so sick. That would be like putting lights out right there, bro. Like, none of these other algorithms would be able to compete with me. Period. Because then I can run the neural network. So I got a neural network that corrects the random numbers that I train up, and it's the algorithm is called LoRRC, low rank recurrent convolutional random number generator. So we're using a LoRRA based neural network, low rank adaptation, and then I'm attempting to use a 9x9 neural network that's split into half. So we're only going to be working with, like, you know, 40 neurons that we're splitting up into 5 layers with some, like, you know, as compact as you can get it. We'll see. I might have to do 10x10 split in half. So that'll be like 49 neurons, which takes, you know, a decent amount of time to sum up and divide, but should be pretty fast. So if the pseudo random number generator fails, so we take the running XOR from all the after the division instruction, we're running XOR that, and then we rebound that number when we want to use it between -1 and 1. So the idea is, when we do our running XOR, that we're going to do a running XOR. So the mantissa bits, when we do our division, are going to be a lot more random, because, you know, if you just think about, you know, like, we're going to do a floating point division. Okay, I'm going to divide. We got the hidden bit with the mantissa. And the key thing that you got to understand about that is that in floating point, all numbers that have a floating point exponent greater than the number of mantissa bits which for a 64-bit floating point number is 52 bits. For a 32-bit floating point number, it is 33 bits. Is that right? 8 plus 1, 9. No, 21 bits, right? Oh, I can't do math in my head, right? No, 9. 23 bits. Yeah, right. 23 bits. I can do math in my head. When you're doing engineering, you can't just like rely on remembering the numbers. You have to rely on like how you calculated the numbers and be able to recalculate them from scratch. That's a good little piece of engineering advice for the day. So what am I saying? We got a recurrent neural network. We're going to generate numbers. Oh yeah, the mantissa bits. So when you do a division, the divisions, the exponents will not be random. But when you start to XOR the mantissa bits, though, it gets very random, because when you have randomness, you got to understand most of the bits are going to be like the zeros in the MSB or LSB or whatever. Let's take the fractional bits. Like I got 0.0001, right? The number, most of the times, those bits up in the top are going to be 0. But only for like the first, some number of bits will they mostly be 0. So the bits in the LSB, when you're making a random number, don't really matter as much as whether or not the numbers that are in the, like if it's 1 point in floating point, it's going to be .00001, 0.0010100, something like that. These fractional bits, the ones that are less than 1, are going to be much more random than like the integer parts. Like if I was going to generate a random number and I wanted to generate an integer, it's a whole number, then that I'm going to need a much more complex algorithm with, as opposed to like working with values between -1 and 1, which I could also work with numbers between 0 and 1, but you get an extra bit of precision when you go -1 to 1, and I can use the Marzangolo polar method, Marsaglia polar method, the pseudo-random number generator sampler method that works. Is dependent, the accuracy of this is going to be dependent on the pseudo-random number generator that you pipe into it. If your pseudo-random number generator isn't that good, then this algorithm is not going to work as good. But this is some excellent mathematics to learn. If you want to learn about statistics, watch that 3 brown 1 blue statistic video where he's talking about how the bell curve, you think of the bell curve in 2D, it can actually be in 3D. You can rotate it around, because in order to get your statistical probability, you got to do 1 over the square root of pi, I think, right? Yeah. You got to remember the concepts. I'm just going off memory of the concept. So you've got the area, you need your area under the curve to be 1. But if you do it in 3D, you only multiply the value by 1 over pi. So what I'm going to do is I want to use this technique with my LoRRC random number generator in order to, instead of using a 2D polar method, I would like to use a unit sphere so that I can avoid doing the square root of pi function. Wait, hold on. Hold on. Let me walk that back. I'm not going to have to calculate 1 over the square root of pi here. Okay, change that one. Change that. But hey, we might still want to do it. I still want to see whether or not I can actually figure this out, because this is really cool statistics. If you want to learn something about statistics, go watch this, because this is some calculus optimization using some trigonomic stuff. Some trigonometry stuff. See, here's the nitty gritty. This is it. You got a sine and a cosine, and then you got to think this is like on a unit sphere. Sorry, a unit circle. We were not in the sphere yet. We are in 2D. You take two random numbers, -1 to 1. Square S. Okay, I'm not gonna like put too much more time into this, because I've taken about as much time as the last video that I deleted. But I think I did a better job of explaining things, because this is a very complicated thing. There's a lot of mathematics in here. So this is cosine 2 pi u. This is imagine you got it's a complex number. See the I right here? It's basically what is you see what this is? This is the trigonometry identity. See the R e to the IZ. All right. This is equal to here. This is the Euler's identity right here. Ba-boom, ba-boom, Euler's. And then what is the -2 ln? So we see a 2, so we know it's the derivative of this. The answer, well, hold on. What is where'd the ln of u? I mean, you could figure this out just by looking at it if you know what Euler's identity is. But where'd the ln sneak in from? Direct application. X is equal to what? Is it because it's oh right, because this is the inputs are from -1 to 1. So you look at the logarithm is where's the logarithm? Oh wait, we want to look at a graph. All right, see this? See how this is from? It's from 0 to 1. It's negative. So you take advantage of that, because the input is -1 to 1. So we're scaling. We need to like make that work with the sine and cosine functions. So where's the ln of? Okay, so u and u1. What is u1 again? So -2 times, what is that going to do? Trying to think mathematically what this does. The -2 ln s over s. So ln s, what is this going to show you? The break. Oh, it's s to s to the negative 1. You're like, gotta think it's like, and then we're taking an antiderivative, right? What's the antiderivative of ln? Is x ln x minus x. Isn't that what they're doing? I think it has something to do with this. And then this turns into just s, because we went from s to the negative 1. No, they took a derivative. So it's like 2 times x ln x minus x. And what does that do? So x minus x is 0, right? But x... Oh, you just pull out the x minus 1. So the ln x minus 1. So then you got to look at the bounds. Right? So I need to bound it, rebound it. So it only works on a certain bounds, right? And then outside of that, then it's not going to work because it's starting to level off. Okay, I want to get to the coding though, because this is a total. This is a negative 2, so then it goes up to like do the antiderivative, right? And then you get 1 over s, which then makes it a ratio. It makes a lot more sense if you watch that video from 3 Brown 1 Blue, where he takes the statistical bell curve, turns it 3D. You just look for a bell curve in 3D on his thumbnails, and it'll make a lot more sense. Because honestly, like, this is like a load of calculus that is, while not the most conceptually difficult, this isn't anywhere near as hard as the quantum physics that I'm learning. It's definitely tricky. But you can recognize, like, you know, once you know I'm working with Euler's identity, like, all right, cosine, sine. And then, so what's the natural logarithm of u is like, it's like the x and e to the x minus 2 times minus 2. Well, it's bounded now from, because it was, we're in a range where it's always going to be negative. Okay? So when you did the minus, you've made it positive, and then you multiplied it by 2, which means it's from 0 to 2. And then we're taking square root, you know, it's like square root from a value that's between 0 and 2. And then multiplying that times the cosine. Oh, because you're rebounding it. Right. Okay, so this is a rebound. Right. Yeah, no, this makes sense. So you got to understand, the input's -1 to 1. And then I'm translating this into positive value. So I multiply negative. So the range is -1 to 1. So, but that's a range of 2. Okay. Does that make sense? Now that makes perfect sense where you're coming in from this. So it's ln of u is like, we got e to the x, and then we're trying to find the x, right? And then it's -2 times that x. And what are we working with? And then the e to the x value is now bounded between 0 and 1. No, 0 and 2. So now we're taking the... so it's like we took a value between e to the x from the range where it is negative in this curve. Right? and it's negative, goes down past -2. So we multiplied it by -1. We like basically flipped this graph around. And then we multiplied it by 2 because the input has a value, a spread of 2, because it's -1 to 1. So that totally demystifies it. It sounds so complicated. When you look at the calculus, like the calculus proof behind it, that's pretty complicated. I think conceptually this algorithm works a lot simpler than the math proof. The math proof is like, let me watch that one again. First time, like if you haven't looked at integral calculus in a while, and then you look at that, you're like, what'd you just say? Huh? All right, so I'm not going to get any programming done. That was like quite a bit. It was like 46 minutes of getting hit with quantum physics and neural network calculus. Sorry about that. Difficulty level, that was definitely, like maybe you would, I mean, it depends on what school you go to. Like, maybe a senior in an AI program might be able to understand that pretty well. But if you go to a good school, like maybe a junior might know that nowadays. If you went to one of those private schools, like Northwestern University. All right, so let's look at the what do you call it? The seams. Where's the seams? Didn't I open that? No. So we are where? Crabs BSQ? Oh no. Why do I have Crabs BSQ? Seems like because it's just easier to evaluate an expression. All right, that makes sense. And then we got a room after that. And there's the matrix. Okay, and then maybe, see, it seems like the random number generator needs to go after the matrix, because I've just been spoofing it this whole time. I've just been, because it's like, you got to look at, this is like the order that I'm building up the API. So like, this thing is from the ground up. I'm crazy, bro. Like I don't use the C++ standard library. I built everything from scratch. Like a fucking lunatic, bro. Like a madman. With my middle finger up in the air at big tech saying, F you, I'm going to take you down, bro. Even going down with the ship. My last dying moment was flipping off big tech. I don't know. I've always been like that, dude. I don't know, man. I'm just kind of... Life would have been a lot different if my hard drive hadn't melted and destroyed my API. I had my own API back in the day. It would have been... I was trying to make the first Linux package manager back in the day. I had a Java-based system. It would have been more like Android. But yeah, it was more than I could chew at that. Yeah, I wish I had gone to an engineering school. So it's a little bit difficult for me to sneak in. It's like... Let's look at the random number generator, see what it's like. doesn't really do anything. Random seed. Okay, so this is just not even... I didn't even know what I was doing when I made this. I knew nothing about... I was like, when did I make this? I think I had not even taken a statistics class at that point in time. Now that I think about it, I'm zooming back in the history. It's like, oh, I had no idea what was going on here, huh? Okay, so I mean that's fast pseudo random number generator, but I'm not rewriting that. I have a completely different algorithm. The hell? I mean, it works. The thing is, like, I need to plan ahead. I need this LoRRC algorithm. Where do I have it? I can open that up. I have it in TypeScript, but it's not fully finished. I don't really want to like port it from TypeScript over to... Why is it in TypeScript? For the SubsecondId. Dude, it totally took the project down though. I have a new 64-bit UUID library. And then I'm like, alright, gotta go next level, bro. Neural network based random number generator with the fewest number of division instructions. Yeah. That's quite a bit of work though. Where is that? There's SubsecondId. Yeah, it's unfortunately it's common pattern for me to get sidetracked. What am I doing? I got a memory map. I've switched all my memory maps. Well, I am switching my memory maps to grow down. Like a push down automaton. Or automata. I'm sorry, I'm the weirdo. I say automaton. And then I diss on people for saying aluminium. So we have I store the dirty inputs just for statistical calculation purposes, but I take the input and then I XOR it with the running XOR, and then I rebound from -1 to 1. So we keep track of the last 12 inputs. And I split the neural network in half into an A and a B layer, which I split up using a low rank adaptation into a variety of neural network split LoRRA, split in the diagonal neural networks, and then I utilize portion of the LoRRA for different neural networks. what does this allow me to do? It allows me to... How would this benefit? So I think the way that it benefits is I share I think the diagonal is the layer that goes from the input to the first fully connected layer. And this allows me to I might have to throw it out. I don't know. It might not work because of the way the LoRRA works. So I take in this example, I is what? What is I? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 9x9 LoRRA, low rank adaptation. So I take two 1x9 vectors and I multiply them together to get I multiply one of the vectors by the transpose of the other to get a 9x9 matrix. And then you add that to your neural network. And then after your neural network, you train your neural network like normal. And then after your neural network is trained, then you use this LoRRA technique to essentially feather the weights around. It's kind of like I don't want to call it a fuzzer. It's kind of like what you would do with a fuzzer, where you explore the area around the values randomly. Kind of like that. A little bit. Fuzzer's not the right word, but maybe that could work to explain what I'm doing. So like the neural network generates multi-dimensional space. And then once it's set up, the neural network values are like a random seed for my random number generator. So we want to change this. So instead of just inputting the neural network or the random seed, we're going to do this LoRRA technique with the neural network. And this is going to correct values that do not form a normal distribution. So if a generated number using the pseudo-random number generator described earlier with the running XOR, if that fails, then we're going to run this algorithm. So when you do your, let's call it X times Y transpose LoRRA multiplication, you get this thing where the diagonals are the products of the rows of the X and the Y vectors. So imagine we have a matrix that's U1, U2, and then V1, V2. Wait, let's make three. U1, U2, U3, and then V1, V2, V3. Okay. So then the diagonals, I'm going to get V1, U1, V2, U2, and then V3, U3 in the diagonal. Because it's, your basic matrix multiplication of a vector times a vector transpose when the vectors are the same width. Is that the right word? Dimension. So I don't know what this is going to do. I have this set up to where the diagonal is a neural network layer. And then here, this is layer 0, 1, 2, 3. And then same for the B. We got 0 because in my mind, what I see is that the transitioning from the neural network input to the first fully connected layer is it's an abstract function. This abstract function is going to work best with the most number of neurons because it is an abstract function. So the magic in the neural network comes from the deeply connected layers in how the weights are stored related to the other weights. It's not, the magic does not come from the like the input layer. But you can get an approximation with the input layer. So the input layer is supposed to refine the inputs into the language that the deep layers understand. And the deep layers, they're going to have the ReLU activation function to avoid vanishing gradient problem. And then the input function is going to have to take values that are between -1 and 1, which means that I'm going to have to take the input layer is going to have to be a sigmoid activation function. My prior version and what this is saying is stuff about a determinant, but we are switching over to the dot product because I've determined that that was bozo, and I totally should have never even wasted any time with the determinant. I didn't listen because I'm kind of stubborn. I have instilled this trait into my child, and it's kind of frustrating to deal with. But the the inputs the sigmoid because why? Because the input is between -1 and 1. Wasn't I going to do a dot product? I forgot about the dot product. I don't remember. I think I was like going to do... Oh, I'm trying to do some dimensional reality reduction, but I don't know exactly what I'm going to do. We're just going to have to remove... I'm just going to put a note. Alright, so I, for some reason, thought I could use a sliding window determinant function. Oh yeah, that's what I was going to do, the dot product of the... So I have the inputs and then I have the outputs. There's my memory map for the low rank recurrent convolutional random number generator. So I was wanting to, reduce the dimensions? Then feed it into a neural network? I don't know if that really makes sense, though. You gotta think about it. Like, so I got the last 12 inputs. Okay, and then I want to do a sliding window convolution function, and then run that into a neural network to reduce dimensions. Wouldn't I want to just do something with the other numbers and then take the input and dot product it? Because, let's think, I got 12 inputs, and then I got 12, 2 sets of 12 outputs. And then let's say I want to reduce these dimensions. And then I've got a fully connected layer of perceptrons. So I want to take the input and then translate it to the language the LLM speaks, or sorry, the neural network speaks. So the dot product. What if I could do some trick with this polar? No, that wasn't it. This polar technique. What are they doing? A squared plus b squared. It's square root of a squared plus b squared. Basically, with the stats. The bell curve. And then this is... I was so confused by this. It didn't make any sense. I think it just went in one ear and out the other, because, dude was, showing a math proof. And there's one YouTube video that goes into detail about this. And I thought this had something to do with, the calculus. But really, this is just a scaling thing. Going from a -1 to 1 input to a 0 to 2. For our statistical purposes. Because we can't have negative lengths, because that's not, a thing. It's not a tensor. A negative length is not a tensor. It's an artifact. Is this it? This is just a Pythagorean theorem thing with a unit circle. So you got to go back to the triangle. If you could just remember this drawing, it's a lot easier to remember. This is where it comes from. And then r squared is u over rv over r. Alright. I'm biffing it hard on this live stream, dude. It's just really complicated stuff, though, dude. I don't know if I could really, like, explain any of this stuff any quicker, dude. I hardly understand it myself, so you'll have to forgive me. I can hardly do this, dude. What happened here? I think I just need to take this back over to here. My name. That's what I want. What? I don't think that AI code complete actually helps, dude. I think it makes you slow down. You know, people like Vim freaks, like, they could just type that stuff out so fast. It's not even like a thing. Oh no. Oh, did I redo this? I think I'm forcing them to use 8-bit context types. And then if you want to use 16-bit context types, then you have to use all the other context types. And, you know, likewise for the other types. I don't know. TA type. Size of. Anything else has this? T size of? What would TA mean? It would be ASCII. TA is ASCII data type. It's right here. I like to go sort by the line. Oh dear. TA type size of. So this is a type size of function. Is it in here? What is this? See how. Huh? This is like the first scene, right? The second scene? I don't understand. I'm just confused by that. I mean, they're both supposed to be. I've never had this problem. It seems like I would have had this problem a lot in the past. What's this? Estimate. Everything's fine. I hate it when I come back to a project and things are broken. I'm like, what the hell is this? Type of. The hell? I've never seen that. That was a new one. The one I'm looking for is not here. And then there's one that I've never had there. It's, what am I looking for? I'm looking for the output. I mean, it might be in the output. I can look through the output. It doesn't matter. Identifier not found. So there's no like templates. It can't. What do we got coming in here? Array. Does it call it array? What the hell? What do I just move it over to the other location? I could just move it. Oh, shoot. I should have kept track of where I was at. What? Nope. Oh, because it doesn't. I'm looking for the wrong one. Here it is. I think I could just put this next to the A-type size of POD. Does that fix it? A-type size. Oh, yeah, that fixed it. Cool. Okay. Type of. And what is this like? Also, too. What the hell is type of? I don't know why it's doing this though. I probably shouldn't be. Because this is the A-type HPP. Alignment mask. Okay, so I'm not doing this. This is dumb. Yeah, this is just dumb. This is some. It should be here. Right here. You just make it in line. In both. Where you go? We just tell those C++ standards committee people they can go suck it. Just tell them we're not having their bullshit anymore. Like, dude, it's just ridiculous. It's ridiculous. Everything about it's ridiculous. All you gotta do is just only use one header or one CPP file. You don't even have any of these problems, dude. The number of problems it solves in C++ by only using one CCP file is gigantic. It's like this, the very idea that this is even thing that I even have to think of is just stupid. And the thing is, okay, so the inline, you see how it's got the inline? So that won't do anything when you do a declaration. So the declaration is just declares that this thing exists. It doesn't say anything about whether or not the compiler should inline it. So the prevailing logic is that you should just define it in with the headers. Sorry. Wrong word. With the template code. But it doesn't really make sense because you just use one CPP file and then it's like, so what if it doesn't? So what if this doesn't do anything? So what? I mean, the C++ standards committee want me to put a const after everything that is like const. It's like not there. I mean, but or sorry, that wouldn't even be it. Const. They want me to do that after like all the things, not necessarily there, but you get the point. I hate that. I think it sucks the fun out of it. I just don't care. I don't think that that's going to change the reliability of my code. It just makes it a pain in the ass. And how the hell am I supposed? Why should anybody care whether or not you stick the inline in the header, like at the declaration here, or if it only works here? Like, it's just nobody wants to deal with a rule like that. That's the kind of rule that really just makes people not want to program in C++. But unfortunately, people suffer from the leave Windows because they want you to log into OSS. Or, hold on. What did I just do? Because they want you to log in for OneDrive, so I should, like, switch over to Apple. Which is the most stupid thing I have ever heard, dude. Like, so you're upset that Windows is making you log in. So you want to go switch over to Apple, which makes you log in and also pushes iCloud on you? Get out of here! That's the most stupid thing I've ever heard. Just switch over to Linux, man. I mean, leaving Windows is not the most stupid thing I ever heard. But like going over to Apple because they're more like Microsoft is more like Apple now. I mean, it's just ridiculous. I mean, just log into OneDrive. Just don't use it. Don't pay for it. I don't know. They'll try to sell you on Microsoft 365. I think I'm gonna not pay for that anymore. You know, just don't pay for it, dude. All right. What problems do we have now? No, I think I just fixed that one, right? Uh-oh, alignment mask. What the hell? Did I accidentally take out more? It says it already has a body. A-type X. Did I miss one or something? Oh, right. See, there's like a computer science problem going on here with the C++ thing. So in C++, it's going to compile as fast as possible if you split up your code declaration. So if you can import a .h file that doesn't have any declarations in it, it's going to be a lot faster than compiling anything. So that's just what you do in C++. But then it's trying to separate the public and the private API is kind of a disaster in C++. I just don't bother. It is a royal disaster to make modules in C++. And the modules, whatever they came up with, it's not... That ain't it. Alright, C-type map. Uh-oh. What do we do? I don't understand why it's split up like this. See how it's the first scene. Problem with the neural network based random number generator is I definitely could not have that here. I use this for testing everything else. And then I was supposed to circle back and then implement my own random number generator. That didn't happen until like recently. But in order to do that, I need the matrix. It would make sense to just bump this thing down to here. I've never really been very happy with how this is here. So in order to be, I wish that I had not made everything from scratch, because, you know, writing my own integer to string algorithm and the floating point thing, that thing's like a can of beans, bro. Then building up the uniprinter. I mean, well, you got to start somewhere, but it's kind of like a chicken and egg thing. You really want to test your integer to string algorithm and your floating point algorithm. You need the random number generator. So, but I want to put it down here because then I need the neural network. And the neural network API is... this isn't like a machine learning API. This is like a core API to build other APIs with. It's designed specifically to not be the only API it's built with. It's designed specifically to be the core of APIs for any language. So having a machine learning library in here definitely off limits. It's outside of the scope of this project. But it is definitely inside of the scope for a starship. So pretty much I need to fix this. I don't understand why this is grayed out, though. Oh, the room seam. Is the room seam not right? Well, why is this not like this? Because this just shouldn't be like this. This is the first scene. maybe A type. Does this thing, is this, does that fix it? I don't understand at all why this is doing this. Oh, it did something. I don't know what it's doing. Because this is like the first seam, so why would it be like that? Room seam is 17. Oh. Gotcha. Uh-oh. Great. T hash. What the hell? What is it? Hash prime? Hash IUB. Do I really have to put this? Clearly, there's probably a reason for why I did that, but I don't like that. T hash. Oh. Wait. Is it prime? Shows to show how long it's been since I worked on this. Return being read. UV. No? Well, that doesn't make sense. Why would it do that? Minus the size of what? Where do I read it? What is this IUA here? Is there anything else I can figure out? There's a bunch of those, but C. Oh yeah, I've been looking at this one for a while. I can't figure out why this one can't find the C out. Everything else at work seems to work just fine. I don't understand that. I don't understand how it can say identifier not found. Well, it's right here. This one should be easy to fix. What is this? Oh yeah, I have to add that with the isn't this the error byte? 1, 2, 3, 4 params. 1, 2, 3, 4, 5, and then error byte. Okay, where's the error byte? Let's just look for the last time I did the star. Load the 4 type. Params index. Shouldn't I be like and then it goes into a bunch of blah. What is this shit? Oh, the variance, right. So this isn't, I don't see, that's the sheer, I'm getting exploding complexity right here. And I think I opened up some exploding complexity and then quickly slammed that motherfucker back shut and kind of just moved on as if there was no problem. Which I don't recommend you doing, but that's what I did. What are you going to do? Sue me? So DC out. Where is it getting DC out? So I'm in release. Am I? Is it not in here? Maybe it's not in here. Oh. Do I need to do... DC out errors, where that's at? I think this will do it. All right, sweet. 2 more gone. Illegal function definition. Damn, bro. Shit. It's lit. Expected a semicolon. I was expecting it to be lit. Okay. And this is wrong how? Context map. Probably just need to add this one to BOut, right? Huh? Oops, wrong one. Is that it? That's it. Okay. Since I can't read, apparently, I guess we're just going to replace the whole thing with a copy paste. How does it work? Oh, BOut terminate. Can we get rid of that one too? How about BOut reset? Oh, damn. Shit, son. We'll just stub those out and move on. I don't like seeing errors at this level. See out? What the hell? Cannot overload function by distinguish function time will allow. Oh no. Uh-oh. What did I do? No. Man, I broke the internet, huh? Legit broke the internet. Maybe I could just get rid of these errors here real quick. So size, I could just make it go away. Bytes. Now we got origin. This is the error byte. Is this where I'm loading it from? Seems like that would make sense. Origin. What am I loading? What is error? It's the space. Went under where? Is there no error byte here? I mean, it seemed. I mean, that's one option. No, that's not right. Undefined. I don't like the way I laid this out. I had an immature knowledge of what was going on. I don't know. I think I switched over to using the if-def, right? Being params, args, context map. Params, args, and then context map. Okay. Being read. I'm gonna have to have the context map. Be all one way or the other. Where is this at? PC. What is this? What is this? Don't use speed. Never seen this one before. Local functions are illegal. What does that mean? Does that mean like I... So I'm missing a curly bracket somewhere. here or something. I don't know. I don't know whether or not I believe that you should enclose all these guys. I'm gonna have to think about it, because there is a dangling else. It actually is a thing. I don't know what to think. BOut error. What about the... This one has the start button. And then... I don't think that would even make any sense there. What is it? This doesn't make any sense. No. Never mind. I don't like exploding complexity. There's a bunch of stuff I just saw that I have to make iterations of permutations, and I'm gonna have to do something about that. I wonder if there's anything that I could... In general, when you're in a situation like this and you don't know where to start, you should start somewhere with something you can do. Here's something I can do. Must have renamed it, and then the other code was commented out or something. Low hanging fruit over. This, what is it saying? Is here. All right. It's lunchtime for me. I don't know what I want to do. I'm feeling fat. BOut is not a member. That's not true. Yeah, what's going on here? What is this? TS print string. Okay. Well, I don't understand that, I guess. Guess I'm too stupid to be a C++ programmer. Huh? Still at 113. BOut. What is it now? Nilp at the end? Uh-oh. What did I do? Oh, it's the context. Right. I don't know if I want to, like, say that. I could get a couple out. Local function definitions. Okay, these are all the same error that are not really an error. Now this one I'm baffled by. I don't know what's up with this. Let's go back to the other seam and see if I've destroyed everything. Oh no. Destroyed everything, huh? Damn you. Undev. Why is that squiggly? Oh, right. Undev. DCA. Oh no. Hey, actually went down one. Still don't know what's up with this. I'm gonna have to take some time on this. There's 109. It's not underlined. I'm so confused. Why I can't find the cout. Do I need to? Unfortunately, it's because I haven't been programming this much. How did that happen? So what do I think happened? What do I think happened? I think the what do I think? I think a break would be successful for me. I covered a lot of stuff. My brain's still kind of frazzled. All right. Well, hey, I'm gonna go eat lunch because I didn't eat breakfast and I ate too much last night. So I think Maybe I should wait, even though I need to starve myself. Thanks for tuning in. Until next time, farewell, au revoir, sayonara, peace be with you.